Everyone, welcome to the online version of the cast, and this is going to be lab 9, and in this lab we will be talking about code generation, more specifically code gen.scala. Basically, in this lab we are done with the front end phase of the compiler, and if you remember, the last thing we were working on in the front end phase of the compiler was semantic analysis, which was PA5 and PA4 and PA5. And in this lab, we'll be starting to work on the backend phase of the compiler. And if you remember from lecture 1, the backend phase of the compiler, there are two important things. One is the code generation, another one is the optimized code generation. So codegen.scala and optgen.scala. And so in the optimized code generation will be PA8, and because we lost the week because of the virus situation, and so we may need to skip PA8. But okay, but let's continue and let's start the lab. And the ultimate goal of this code gen.scala is given a populated ASD. So remember, we generated the ASD in the parse when we were parsing the code, and we populated the ASD by deriving some properties, some attributes. And so given this ASD, this populated ASD, we want to output a MIPS code. So MIPS is a very simple to understand, very straightforward assembly language. And there is a simulator for MIPS. It's called SPIM, and it's already available on Andrew. And there are different simulators for MIPS. So there's one available already in Andrew, so you can use that. And okay, so if you have taken CS315, you should know MIPS by now. But if you have not taken CS315, maybe you should review MIPS to understand what's going on. So let's do a quick overview of the MIPS, what's going on. And so let's go over here. And there are two, MIPS code has two sections, two important sections. There's a .data section, there's a .text section. So the text section indicates that the following items are stored in the text segment of the memory. The data section means like whatever follows is stored in the data segment of the memory. So this data and text, they are called directives because they start with a dot. And there's another top level directive that I didn't say. It's called .global. .global declares the symbol. Symbol is global, which means that it can be referenced from other files. So so again, .text is where we put the code. .data is where we put the static stuff, like all the literals, integer literals, string literals, or whatever. And .global means we declare something as globally defined, so we can reference it from other files, other .s files. So the extension of the MIPS code is .s. And so if you remember lecture 1, we talked about there is something called cool runtime.s, which is available in the lib folder, excuse me. And in the cool runtime s, we use some variables that are declared globally in our code. So basically, when we compile the code, when we compile our cool code, we create a mips.s file, and then this mips the .s file, like if you have a main file, main.cool or whatever, something.cool, and then when we compile it, we create that something.s file. Then that something.s file with a cool runtime, we can use that with SPIM, which is a simulator for MIPS, to be able to run it. And in the cool runtime, there are some interesting things. The one important thing in the cool runtime.s is a garbage collector. So we need to make sure we put appropriate flags, everything for the garbage collector to be able to work properly. And okay, and so let's quickly go over the MIPS. So in MIPS there's things called registers. Registers are like a small set of datas, And it's not a complete slide over here, but what's happening is that there are some T registers which are temporary, and then there are A registers, .V registers, SP registers. So temporary registers or T registers are just temporary. You are not gonna use them for we are not gonna use them for this code generation, but we will use them for the optimized code generation. We will take advantage of them. And so in the just basic code generation, we want to get something going. But in the optimized code generation, we want to use this temporary to avoid spilling the registers into memory and then unspilling them back. Okay, and again, T registers are temporary registers, A registers are like function call arguments, V registers are return values, SP holds the address on top of the stack, address of the top of the stack. And there is something called system call. Calls are like built-in functions that we can invoke them by using the syscall keyword. Again, the registers start with a dollar sign, and that special register called register 0 always holds the value 0. So make sure you review those very important stuff. Registers hold some are like temporary, holding some value, and make sure you review those. Review what's MIPS. It shouldn't take long. Okay, let's continue. So this is a simple MIPS hello world program, and you can see there's a .data section, and in the .data section we allocated a string literal hello world, and then we can use this string literal by a label called out string. So out string is a label. Labels are like addresses, and addresses, remember, we are talking about a 32-bit system or 4 byte. All the addresses are 32-bit or 4 bytes. So label of out is so what we did was we created a data section. So all the static stuff we allocated a string of hello world, and it's a .ascii z. So .ascii means just ASCII, and then z means it's null terminated already. And so we will talk about like what's going on when we do code generation. Remember, we always need to uh, we need to null terminate the string. Um, Otherwise, like the system call for will just keep going because there's no null termination. Again, so when we allocated the string hello world, we assign its address. So somewhere it's allocated somewhere in the memory, and then we can reference it by using the label out string. Then we created a .text section, and then we have a main, which is a special label, so it's the start of the code. And then we put 4 into, so li means load immediate, and then we put 4 into v0, and then we put out a string label into a0. So we put the address of the outer string, which is the address, we put it into a0, and then we invoke system call. So system call is like a built-in functions that are into MIPS. So one special system call is system call for. This system call for prints a string. Then we use another system call, which is interesting, system call 10. It terminates the program. So remember, when we put some number into v0 and then we invoke system call, we are calling some built-in function. Okay, so let's continue. And so in this lab, so remember, make sure to get the handout from the CAS website. But in this lab, we will be talking about so what do we need to create in, what do we need to output in our code generator regarding the .data portion of the MIPS code. So anything in the .data, we will be talking about it in this lab. So what should we put in the data section of the MIPS code? So we're gonna put things that are constants, like string literal, int literals. They're all constant. So we can declare them in the data, and that's the subject of this lab. We're gonna talk about how we're gonna output these things, and then what's the layout going to be. So another thing we're gonna talk about is like object prototypes. So object prototypes are like recipe how to create a new instance of an object. Okay, so let's start by int literal. So in this int literal, we can see the following, and we have dot word -1, which is for a garbage collector, and then we have an int literal of 13. So 13 doesn't mean dot int literal of 13 doesn't actually mean it holds the integer value of the 13. It means it's a 13th int literal being outputted by the program, by the compiler. So 5 means it's a class tag number. So it's like an arbitrary number we assign. Okay, from now on, integer class has a number of 5. And then dot word, so again, dot word means some 4 byte, 4 byte. And then the next one, 4, is the object size, so integer 4 byte, makes sense. And there's a dispatch table of int dispatch table. So remember, the addresses are 4 bytes too, and then we put that there, and then 20 is the actual value of the integer. That's what's going on here. And then -1 starts all over again for another int literal. So that's somewhere after here. But again, addresses are 4 bytes, and then dot word is, we are saying, it's a directive saying that we're gonna put a 4 byte somewhere, and then yeah, makes sense. Let's continue. So let's talk about the string literals. So string literals is kind of a little different, but it's basically same idea. So -1 for the garbage collector, and then 3 for the class tag number, and then 10 means the size of the string literal, uh, like how much size is it taking. It means 10 bytes. And we put a string dispatch table, the label, so we can go look it up. So again, labels are just addresses. They don't mean anything. They're just addresses for the program, for the MIPS. And then we have an int literal, which is the size of which is the size. And then we have a dot ASCII, which is the string value. Remember, it's dot ASCII, not dot ASCII Z. Dot ASCII means just a ASCII, but not a null terminated. And it's not a null terminated. If you have dot ASCII Z, it's null terminated already. So there's a 0 somewhere in the end. And then we have dot by 10. So if you remember, 10, ASCII value of 10 means it's a \n or new line. And then the last thing is dot byte 0, which is a null termination. And then we have a dot align directive. So again, anything dot means that it's a directive. Two top directives were dot data and dot text, and then another directives we can see here, dot byte, dot ASCII, dot word. These are other directives. But what is dot align? So what's happening is that when we say dot align of true, we are saying that everything has to be in the word boundary. So whenever I say word in MIPS, I mean 4 bytes. So everything has to be in word boundary. So the next thing should start from the beginning of the next word. So we cannot have like we cannot stop something somewhere in the middle of a word and then start something in the middle and like somewhere in the middle. Everything has to start in a word boundary. And then that align to, it means just make sure the next one that's gonna start is aligned to 2 to the 2 bytes. So this doesn't mean to 2 bytes, it means 2 to the 2 to the power of 2 bytes. Make sure the next one starts in the next word boundary. Makes sense so far? Okay. So again, 2 to the 2, because the MIPS is 32 bits and 4 bytes. So yeah, let's continue. And another thing we are seeing here is called cast name table. And cast name table is like a dump of all the string cast names as a string literal. So let's go back. So let's go back to the beginning of here. And so if I have an int literal 13 label, how do I access what is before that? So what's happening is that addresses in MIPS are 32-bit or 4 bytes. So if I have the address of the int literal, so again, int literal is a label, so I can have address of that. And then if I add 4, I get to the line after that, the line after that, which is dot word of 4. So labels, they don't actually have any address, they don't hold any address. So just when you see a label, so MIPS doesn't have a compiler, it has something called assembler. So whenever it sees a label, just ignores that. Labels don't mean anything. What is happening is that when we have an int literal 13, what's happening is that dot word of 5 has the offset of 0, and dot word of 4 has an offset of 4, because again addresses are in bytes. And then int dispatch table has an offset of 8, dot word of 20 has an offset of 12, and so on, so on, so forth. What's happening is that dot word of -1 has an offset of -4, with regards to int literal 13. So if int literal 13 is something, the dot word of -1 is -4 of that. Okay, you now know addresses are in bytes. Labels just don't mean anything, they just say somewhere here. Okay, they don't actually take any space. The labels they don't take any space. So again, class name table, they are like dump of all the class names as a string literals. Okay, let's continue. Then there we have a dispatch table. Dispatch table is like a string of, is like a list of methods available in the class. So the following is a symbol class dispatch table. So all the methods available. So you can see we have any. So remember, symbol was extending any class, and then any class has a method called any, which is a constructor. So what we are saying is that what we are saying is that there's a method in symbol called any, and it's coming from any class. So it's like when we have a class, when we have some class in Java, and if it doesn't extend anything, it's extending an object. And then when we don't call the parent constructor, Java is implicitly putting the parent constructor call for us, but we don't see it, but it's there. It's the same situation here. When we have any, it's actually calling the parent constructor method, and then we have a symbol overrides the toString method. That's why we have it over here. But symbol doesn't override equals method, so that's why we have any.equals. And again, symbol has a method has a method called symbol, which is a constructor for symbol. And then symbol also has one extra method called hash code. So okay, so so we can see that symbol overrode toString method. That's why we don't see any.toString, we see symbol.toString. Okay, so let's continue. So another thing is called object prototypes. Object prototypes are like recipes on how to create a new instance of an object. And so in the following we can see that class symbol has 3 fields: next, name, hash. So again, MIPS is not a typed assembly language. So just for you, let you know, MIPS is not typed. And okay, so symbol has 3 fields: next, name, and hash. And so in the in the object prototype we can see that, so again, -1 for the garbage collector, symbol underscore prototype object, and then dot word 2 means is a class tag number, and which is like a random arbitrary number we came up when we were traversing all the classes. Okay, so the first one is 0, second one 1, 2, something like that. Okay, then we have a class tag number, then we have a object size, and then we have a symbols dispatch table. Then these are the attributes. So remember, we don't know the attributes by name, we know them by offsets with regards to the symbol prototype object. With regards to, so again, everything, we don't know anything by name, we know them by the offset with regards to the label. Okay, so the first one, attribute or field or whatever we call them. So first one is assigned to 0 or null or whatever, and then yeah, so continues. And okay, let's continue. So how, if you have this object prototype like this label, how do we create a, so when I say object prototype, I mean if I have a symbol of prototype object underscore prototype object, how do I create a new instance of object? So it turns out there's a built-in function that we can use, so we can just jump into. So one more thing before we talk about this thing, jump, there's a J instruction, like load address, load immediate, LILA. These are called instructions. There's a instruction called JAL, jump and link. So it jumps to some label or memory address, and it puts the address of the next instruction, like if the next instruction after the jump, into a register called RA. So what it means is that when we jump to somewhere else, we know the address to go back to when we are done with the code. So okay, so in the visit alloc, and which is like a visitor pattern method for allocate some new of something. So what we are saying is that we have the class name, we have the like new of whatever the type name, and then it's a symbol. I need to get it as a string, so convert it to the name as a string. And then what am I doing is that I put the address of the uh, object prototype for this and for whatever the class's object prototype label into s underscore acc. You will see that in the code generator, so let's keep that for now. And then we do jump and link to any clone, which is a built-in method, so you can use. So what is happening is that, so this is how we use this code generator. What is happening is that we are saying uh, acc is like an argument a0. So what's happening is that we are saying go grab whatever that's going on in the object prototype for this type name or this class name, and then we invoke the any clone subroutine which will clone given this recipe, and then the address will be available, the address of the object that's created will be available. So you will see in the code generation. I don't want to talk about it here now. Okay, so the whole idea of this lab was talking about the data section. Okay, let's continue. So one last thing is the offsets. So remember, if you have a label, what is after dot word of 2 is offset 0 with respect to label, and then dot word of 3 is offset 4, dot word of -1 is offset -4. So addresses are in bytes. Good, makes sense. So that was our last slide, and make sure you read the handout that's available on the CAS website, review MIPS, and start working on this homework very early, and ask question. So yeah, it's a very interesting homework. So thank you.